Good morning, year 13s. Thanks for coming along. It's nice to see you, Tanzi. Thanks for popping up on the chat. Appreciate that. Okay, so guys, we're continuing with Carbonyls. This is Carbonyls lesson 4. I know that number 2 in the series is missing. Guys, we're continuing with. I know that Carbonyls number 2 in the series is missing, which is the mechanism, which is a bit of a nightmare, really. And I'll try and add that in when I get a moment. Free, because it is nice to have a complete set. It's like Pokemon, you got to collect them all. Hey Dixon, thanks for popping up on the chat. Appreciate it. Cool. So I'm gonna switch over to sharing my screen, and we can work on chirality, which will be nice. Okay. So learning objectives for today. Here are my learning objectives. I may not get all the way through this. It might end up that I do one extra lesson. It's very possible indeed. But 4 learning objectives attempting today. So number 1 for chirality is understand mechanism steps with shapes. So in reality, like, we can pick up the lesson 2 mechanism again. I did a mechanism run through in lesson 3 as well, just for those people who've missed lesson 2 because it wasn't live. So next one is know the definition of a chiral carbon. So we'll come to that as part of this, as once we hit to the end of the mechanism. Then understand separation problem, and then drug problems. So, okay. So chirality, chirality is linked to carbonyls for one very specific reason. So if I just move that up to there, we can just draw a line and we can do nucleophilic addition. Nuke add. Let's run a mech. We know that nuke addition is the only thing aldehydes and ketones do. Als and ones. These both do nuke addition. It is all A2 mechanisms are 2-step. So I'll draw my usual, I'll do an aldehyde in this case. Yeah. And we know we have 2 nucleophiles specifically for Edexcel. There are others. And in fact, I'm tempted just to mention one of the ones that was in an exam paper, one where it came up with dimerization. Yeah, the question was actually trimerization, which was really mean. But like I said, there are others in this scenario, but Edexcel want you to know 2 nucleophiles specifically. NH minus, this is the first time you've, they don't want you to use that one. They want you to use lithium aluminium hydride or lithium tetrahydroaluminate. You never need to actually name that, just so you know. And the condition, of course, is in dry ether. It's nice to remember that. And then we also had the cyanide ion. Remember, the charge must go on top of the C. It's a habit of students to do that. That is not allowed. No, the charge must be on top of the atom, which is going to be focusing on the mechanism. And in Edexcels, they want you to use HCN and KCN, which is really irritating. If you're in any other exam board, such as AQA, they're going to want you to use HCl and KCN. Yeah, so just mental note, Edexcel being weird. I don't really think there was any solvent. Was it in ethanol? Might have been, or was it just in solution? Those are the only 2 you actually quote in reality. Under reflux, because of course it's toxic. Under reflux, heat reflux. Okay, so what we realize is when we do this mechanism, we need to now consider the shapes of molecules. So this here, the aldehyde and ketone structure, this guy here is in a trigonal planar arrangement. And you need to know that, guys. Whoops, let's add in trigonal. This is in a trigonal planar arrangement. Now, what that means is it's flat. The word planar just translates to flat. So if I was to draw this in a slightly more like 3-dimensional manner, yeah, what you actually notice is that the entire molecule is kind of flat. I hope you're loving my 3D diagrams here, folks. So the whole molecule around this carbon is flat, is planar. Now, what that means, by the way, bond angles are 120. I think you'll know that one from shapes in the AS. But what this means, I'll actually add that note up here. I'll add it to this guy. That there is 120. Yeah, but because it's trigonal planar, Helmuth, hey boys, it's Leon. Hi, Leon. Nice to see you, dude. God, Leon, you've dropped into a very hard lesson here. It's incorporating a whole lot of stuff from AS, including shapes. But anyway, so because the molecule is flat, what that means is when it's attacked by the nucleophile, it gets attacked in two directions. The nucleophile, I'm just going to put, I'll put cyanide on. Let's do cyanide because it's nice to remind ourselves of that charge. By the way, I still don't like that image. What I'm now going to do is just extend this line to meet them. Yeah, those subtle things that make examiners like you. Here's the CN minus here as well. Now, this isn't going to happen twice. This is not me saying it's going to happen twice. What I'm saying here is, so carbonyl, this is, let's do the notes. This is the answer to the question. Yeah. The problem is you're going to say what the question is. The question is explain why during nucleophilic of this aldehyde or ketone you result in a chiral, in chirality. In the molecule showing optical isomerism. We're going to come to optical isomerism in a bit. I should add that into my learning objectives. But so what we need to, the bullet point here, and this is the nota bene, and it does need, this is important, guys. So bullet point number 1, carbonyl group is trigonal planar. 1 mark. Trigonal planar. Tick. 2nd mark. Can be attacked by nucleophiles. Can be attacked by nucleophiles from above or below. And this is where I really ought to just highlight these keywords. From above or below 50% of the time. Above or below 50-50. Right. So this is because the molecule itself is entirely flat. There'd be no reason for them to select a particular direction. And statistically, there are so many molecules, this is going to happen in this regard. Now, here's the really cool bit. Depending on whether or not it's like the predator waiting in the tree. Oh, no, I disagree, Leon. Predator always comes from above or hiding in the bushes. He never comes up from below. He's always in the trees, Predator. Oh, it's a great film, that. Amazing film. You know they're redoing it, remaking it. Now, because of this fact, because it can be attacked from above or below, something really cool happens. So number 1, the new product that we're about to make, the new product changes shape. It becomes tetrahedral. So if it went up in above, notice, by the way, key things with these diagrams, it must be going to the C. Common mistakes by students. No, that is not okay. This is not okay. Yeah, it must be going very clearly to the C. So when you form this, if it goes above, you know, we get that there, the H is going to be here and the R there, the shape changes. Now, if it goes from below, the whole thing folds up in a different way. So if it comes in from there, I'm going to end up with the O up here. Now, can I just point out, I'm actually going to draw it in a very particular fashion here, guys. You're not really going to like this very much. So here's the nightmare. Yeah. So they look exactly the same. Yeah, they look exactly the same, but they are not. Because these are three-dimensional, yeah, because these are three-dimensional, these are mirror images of each other. Mirror image. Now, what that means is, and here's the bullet point, the nota bene, they are non-superimposable mirror images. So what that now means is, I know it's weird this, and without being able to actually have you guys here to do this with me, it's very difficult for me to prove this to you. It does happen though. There are two different molecules. People think that these molecules are the same. They're not. The word superimpose, what it means is putting over the top. Let's have a go at doing this. So if I draw out, let me just show you this. If I draw out this one, now, by the way, I haven't finished the mechanism, have I? And I draw the other, let's change color. Notice how subtle my change is, by the way. This is a wedge, by the way, and this is a dot. There we go. So the wedge and the line above and below remain exactly the same, but the other two are complete opposites. Now, what this means is if I now try and overlay, let's put a circle around this. If I try and overlay, no, I don't like that. If I try and overlay these, what you realize is that they are not the same because of these groups. Because of, oops, didn't want to do that, that's weird. Because of this group here and this group here, they are not the same. They look like they're the same. In fact, chemists can't actually tell them apart. They're identical from a chemistry perspective, but they're different biologically. So, by the way, just to finish off the mechanism, I hate not finishing a mechanism. What's now going to happen is these are going to pick up H+. Whoops. Final step in the mechanism. There we go. Just make that right there. There we go. Step in the mechanism. There we go. All finished. Going to form a hydroxynitrile. I have to say what an interesting diagram that is to draw. It's a very bizarre way of seeing that mechanism happening in two fashions. But the point being is we can take this off and say we understand that nucleophilic addition follows a trigonal planar starting shape. It then forms tetrahedral, which means 50-50 above or below attack, 50-50 above or below attack, resulting in two molecules, two products which are non-superimposable, and they are said to be, these are now what are called optical isomers. Let's define optical isomerism. Okay, so optical, I'm just going to put my little fan on for my computer. It's getting awfully hot. Here we go. Optical isomerism. So, do you know what? Since we're there, and Leon, are you still in the room? I'm just curious if you're actually going to watch my lesson all the way through. It'd be hilarious if you are. So, organic isomerism. Organic isomerism. So just a reminder, isomerism is split into two. We have structural isomerism and stereo isomerism. So there are two, I'm going to, since Leon's in the room. So just to explain that, Leon, that in organics, something like butane, which you recognize from my teaching you at GCSE, butane can have a structural isomer. Structural just means I rearrange its structure. So I could rearrange it into this. And that there is called methyl propane. Same molecular formula, different structural formula. So we come across what's called structural isomerism. That one there is called branch or chain. Structural is split into three types. We've got branch or chain, they're the same thing. Chain isomerism. We've got positional. We've got positional, and we've got, yes, I recall. We've got positional and functional. Now, just to explain that to Leon, this one here is branch or chain because I've changed the chain length. Yeah, the chain length has gone from 4 to 3. Just to show you a positional. So if I have something like this guy, this is 2-chloropropane, all H's. What I can now do is move the chlorine. The chlorine could go somewhere else. I could put it on carbon number 1, and that would be 1-chloropropane. This is called positional isomerism. Positional iso. And then functional is the idea that you could have propanal, and that end, this is new for you, Leon, because you haven't done A level. That there is an aldehyde group. Yeah, but aldehydes, if you move that double bond O, you can change the family. And this is a ketone. This here is a ketone group. So, but the same formula, C3H6O, C3H6O, same thing, same molecular, but different functional group. So that covers all of these guys. Then we pick up stereo. Now, stereo you did pick up at AS. By the way, if you want the definition for structural, same definition of structural isomerism. Same molecular formula, same molecular form, different structural form. That's it. Different structural formulae. You have to say formula, by the way. And same for that formula. Yeah, and then stereo is different. Stereo is split into two as well. It is split into geometrical. This is alkenes. And optical. This is a new one for A2. Optical. So it turns out, this is for Leon's benefit, alkenes contain a carbon-carbon double bond. Now, carbon-carbon double bonds can't rotate. So if I show this double bond here is unable to rotate, can't rotate. So what that means is there's actually two versions. This is Z12 dichloroethene. There's another version. Because that double bond can't rotate, the chlorines could be on other sides. And this becomes E12 dichloroethene. And that's geometrical. Same molecular, same structural, different arrangements of atoms in space. That's the definition for stereo, by the way. You're interested? Yeah, so two different ones here. Arrangements in space. So optical isomerism, and I'll explain this in more detail next lesson. Optical is a carbon atom with 4 different groups. Optical isomerism. So I've got a H, an R, It really doesn't matter. I'll just put X, Y, Z, and W. All the groups must be different. And what will happen is you will have a mirror image. And these mirror images, notice the only things that are actually changing are the Y and the W are swapping places. Non-superimposable mirror images. And these are different biologically, but not chemically. So this is optical isomerism. I'm going to do a whole lesson on that next time. In my next lesson, I'll do chirality lesson 2, and I'll talk about optical isomerism and the pointless test. So, right, chiral carbon. This is actually linked to my picture. So, you've already got this picture drawn into your books anyway. Now, this carbon here, a carbon, this is a nota bene. This answers my second learning objective. Nota bene. A carbon atom, this is very enlightening, sir, but I've got another lesson now. I'll watch the rest later. See you later, Leon. It's good to see you, dude. A carbon atom with 4 different, and notice my changing color and capitalization. They have to be different. With 4 different groups, a carbon atom with 4 different groups will be chiral. It's called a chiral carbon. And we actually denote this with a little asterisk. So I can asterisk this guy here. There we go. The asterisk denotes that it is going to be chiral. So at this point, I think it's worthwhile having a look at some drugs. Let's do some drugs. Okay, that was a bad sentence. Didn't mean that to come out quite like that. Let's just have a look at some drug molecules. So let's do aspirin. It's nice and easy. Images. I just want them. Oh, of course, it's just a molecule. Better. The question is there any chirality? I don't think there is. There's no chirality. I should explain that really, but it's going to be easier. I know ibuprofen definitely is. Ibuprofen. Mr. Duncan, molecule. Better. Perfect. I really wish they'd just give me full displayed, really. It would be better to do full displayed. I hate the mixture of well, hello there. I will take you. Just seen an image with it on it. Hello, Mr. Ibuprofen. Did it copy? Oh. Can I say PSHE? Don't do drugs. I'm really, really, really bad for you. Right. So, molecules and chirality and chiral carbons. Let's do that. It's easier. It's actually more words. Paste. Right. So this here is ibuprofen. Nice and simple molecule. But the key is there any carbons? Is there any carbons that are chiral? So we'll go through each one. This carbon here, is it chiral? The answer is no, because we've got 3 H's that are all the same. Next, what about this one? This one isn't, because it has this group and this group being the same. Next one, this guy is not chiral, because it has this guy and this guy that's the same. Next, this guy, no carbon in a benzene ring can be chiral because they only have 3 connecting atoms. They're going to be trigonal planar, not tetrahedral. So I can now eliminate all carbons in the benzene ring. The next thing, let's go to the next one. What about this guy? This guy is chiral because he has a H group. Let's draw him out. We've got a H. Yeah, we've got this structure. It's a carboxylic acid group. So we've got a carboxylic acid. We then have this group, which is a CH3 group. And then we have this massive structure, which I'm going to put as R. Keep it a bit easier for myself. So that now is chiral. It is now a non-superimposable mirror image. Let's draw the other mirror image. If you draw these, by the way, you have to draw them three-dimensionally. So I'm now going to convert this into my mirror images. So my mirror images become that wedge and dot, line, C, line, because I want, look, these guys need to be exactly mirrored. So the two solid lines are mirrored, and then the wedge, of course, always goes in the middle. But then you notice that the other guy is going in the other direction. You know, this one here is going in the opposite direction to that one. It's a mirror image. Yeah. Then I can put my pieces on. H, the top and the bottom are always the same. So let's add the CH3s there. CH3. Right. Then we can do the carboxylic acid on that side, and then the carboxylic acid on the other side, and then the R and the R. So there are my mirror images. Now, what this means, so these are now two non-superimposable mirror images, and we now need to talk about what makes them different. So let's just go back to my learning objective. So we can now tick off chiral carbon. Separating issues. Okay, so I'm going to do, by the way, optical isomerism next lesson. So these are now optical isomers. They are going to be described optical isomers. They will be optically active. I will explain that next lesson. Optically active. I'll explain that next time. We will do the pointless test. So what we now need to realize is, so some things that are important to know about these molecules. Yeah, chemically, number one, chemically identical. Chemically identical. A chemist couldn't tell them apart. I'll just to give you a bit more detail, couldn't tell apart. Just to give you a bit more details. Yeah. So melting point the same. Same melting point. So I can't do a melting point test. Same solubility. So I can't check with solubility. Solubility. Yeah, that was a mess. Solubility. Same reactivity. Same reactivity. So I can't tell them apart in a reaction. Same reactivity. Same pH. Yeah. They literally, and here's an issue, nota bene. A chemist can't separate optical isomers. It's very embarrassing, by the way. The worst thing is, isomers, the worst thing is who we have to go to separate these. We've got to go to a darn biologist. Sheesh. And the reason why. Okay, so if these are all the similarities, same, how do they differ? They differ in their biological reactivity. Different bio, in terms of biochemical, biological, different biological functions. I'll put functions, stroke reactivity, stroke outcomes. So, just to explain. So I chose ibuprofen. Yeah, ibuprofen. Ibuprofen is a painkiller, yeah, used by many people all the time. It's a great non-steroidal anti-inflammatory, otherwise known as an Nsaid. Now, it's a great drug for taking down fevers and swelling, good painkiller. But actually, turns out that there are two versions of the drug. We have one version, one mirror image, carboxylic acid, CH3, and then the big R group. I'll do the dashy lines. So this one, I'll just put an R. So this isomer, yeah, is a really good painkiller. Great painkiller. Yeah, great for taking down fever, reduces fever. But the other one, nightmare. The other one, go in the other direction, mirror. Yeah, this guy, make that a dot, otherwise I'll lose the mark. This guy, not so great. Causes side effects, liver toxin. Liver toxin is the main thing. So this one is going to cause the side effects. So one is making you feel better and the other is making you feel worse. Well, in reality, what we realize is that this one is actually more effective than this one. Yeah, if you decided to take way too many ibuprofen, it's this one that'll kill you. Yeah, so overdose death, overdose will cause that, will be reflected as a liver toxin. But if you take it in small doses, the liver is fine to be able to manage it. That's not a problem. So, and we actually sell the drug, and I'll talk about that. Oh, because the mechanism, nota bene again, folks, another nota bene. And this is actually a really important one for drugs. Nota bene. Nota bene. Due to attack above and below 50-50, we make the drug in a 50-50 mix. And this is called drug in a 50-50 mix. By the way, these are also called, another horrible word here. So I've been talking about these these isomers. They're actually given a really special name. These two isomers are actually called enantiomers. I know, I'm sorry, folks. Like, I love chemists a lot of the time, but that one was just horrible. They're called enantiomers. And there's two of them. Now, there's actually two different sets of letters, R and S and D and L. And I can't remember which one that Excel works. I'll come back to optical isomerism later. But we make in a 50-50 mix of enantiomers, of 50-50 mix of enantiomers. Enantiomers. And this is given a name. A drug in a 50-50 mix is called a racemate. Don't ask me why. A racemate or racemic mixture. Either one, whichever one you want to call it. Racemate or racemic mixture. They are the same thing. These are the same. Just other words. So chemists can't separate them, so we don't bother 95% of the time. Biologists can. Biologists can separate them with enzymes. That's how they do it. They build an enzyme capable of eating one of them. Bit crazy, really. It's very expensive. No one ever bothers. So number one separation problem is done. But just to let you know, to add that note to Bene, biologists can separate them by having enzymes destroy one. And then the drug problem in terms of each enantiomer having different effects. I'd definitely say I've come to the end of my lesson today with 9 minutes to spare. So I will end today's lesson at this stage. Come back to here. Hey guys. So I'll leave you be at this point. Tenzi, I hope the notes were okay. And I will see you next lesson, guys, for optical isomerism. And that boxes off then. It boxes off carbonyls. I'll see you guys next lesson. Ciao.